Number 1 says that we have a bacteria population that grows by a factor of 1/4 every hour. And the initial population is 204. What's the growth factor every half hour? So remember, this is our growth factor every hour. So we only want half of that decay factor. And it's not as simple as just multiplying it by a half, because remember, this is factors. And so we want to cut that growth factor in half. So we want what number times itself would get us to that 1/4. So we're going to cut this in half by doing an exponent to the 1/2 power. And so when we do that, 1/4 to the 1/2 power is 1/2. And that's also the same as doing the square root of 1/4. And so the square root of 1 is 1, and the square root of 4 is 2. Then what is the population after half of an hour? So then we would do 204 times the growth factor for the half hour, which is 1/2. And that would get us 102. Number 2, a bacteria population has a growth factor of 3 each hour. What is the growth factor every half hour? Select all that apply. So same thing as the last problem, except for this time our growth factor is 3 every 1 hour. So then we're cutting that exponent in half. So we're doing 3 to the 1/2 power, which again, 1/2 power is the same as square root 3. So A is the growth factor, and so is B after a half hour. Number 3, the equation P of y equals 13,250 times 1.025 to the y represents the population of a city Y months after January 2020. What does 13,250 represent? Well, that would be the population in the initial population, right? So in this case, the population in January of 2020. What is the population growth factor per year, per decade, and per week? And so remember that this growth factor, 1.025, is the growth factor per 1 month. So now if we want to do per year, so per year, we're going to have to change, instead of 1 month up here, a year is 12 months. So for this one, it's going to be 1.025 to the 12th. And you could calculate that out in your calculator. Do 1.025 to the 12th power per decade. So how many months are there in a decade? So remember, a decade is 10 years times the 12 months per year. So this one is going to be 1.025 to the 120th. That's going to be the growth factor per decade. And then per week, so now there are 4 weeks in a month. So now we only want to be in 1 week. So instead of 1 month, we need 1/4 of a month. That would be equal to 1 week. Then part C, does P of y represent exponential growth or decay, and how do you know? So when we look at this growth factor of 1.025, it's greater than 1. So that means that we have growth. It's growing by over 100% each year. Number 4, select all statements that are true. So 64 to the 1/3 equals 4. That is true because 4 to the 3rd power equals 64. So then a third, 64 to the 1/3 power, would get us back one of those 4s. 243 to the 1/3 is equivalent to the square root of 243. That's false because this square root is a 2 instead of this 3. So 243, it would need to be cube root, okay, which would look like this, cube root of 243, not square root. Negative root 15 is a solution to x squared equals 15. This is true. You can just plug it in. So negative root 15 squared, a negative squared is a positive, and then a root 15 squared would just be 15. So this negative root 15 squared would give you 15. That means it's a solution. And then cube root of 27 is a solution to x cubed equals 27. That's true. So if we have a cubed, the way that we undo that is with a cube root or to the 1/3 power. So this would be true as well. Number 5, the population of a city in 1950 was 250,000. The same city has a population of 252,500 in 1951. Write an equation to model the population in thousands of years T since 1950. So we've got to figure out the growth factor. So they give us 1950 to 1951. So here's 1 year's worth of change. So if we look at 252,500 divided by 250,000, this is the change in 1 year. That gives us a growth factor of 1.01. So when we go to write this equation, we're going to want to take the initial amount times the growth factor to the t power. And so our growth factor we just found out is 1.01. And then our initial population was 250,000. And it wants this in thousands. So we're not going to write 250,000. We're going to cancel the thousands and we're just going to do 250. So 250,000 is our initial population. So here would be your equation. All right, number 6 says a substance has a half-life of about 14 years. Fill in the table to represent this. So half-life of 14 years. So after 14 years, it's going to have half its substance left. So we know that this one's going to be 10, half the substance. And then 14 years later, at 28 years, it's going to have another half of the substance. Now, in between these, okay, is a little bit trickier to figure out because now we only want 1 out of 14 years. So now we're going to be taking 20 times 1/2, its half-life, right, to the 1/14th of a year, okay, or to the 1/7th of a year, or sorry, 7/14ths of a year, or 1/2 of its half-life to get these two spaces here. So if we do 20 times 1/14th of a half-life, we'll get about 19 left of that substance, 19 units. And if we do 20 times half of a half-life, or 7/14ths of a half-life, we'll get about 14.1, or 14 if you wanted to round to the nearest whole unit, but 14.1 there. So then when we write an equation to model this, we kind of already have done it up here. We just have to do it generically. So if I just say f of x, then we're going to get the initial amount, which is 20, and then times the growth rate here. And so we can do times 1/2, right? It's half-life. And then this will be x over 14, since it's every 14 years it has this half-life. So that's an equation that you could write. You could also look at the growth factor here between the first year. So you could get a growth factor by doing 19 divided by 20 to just write it for each year. And so then this growth factor is 0.95. So you could write it as 20 times 0.95 per year if you didn't want to have the x over 14 up there. So figure out the growth factor between 1 year. Either of those are fine. Then number 7 says the amount of 2 different radioactive substances remaining after T years are modeled below. Complete the table for substance A. So we can see that substance A reduces by half after 3 years. So we could then reduce it by half to get to this 6 here. Then it's reducing by half every 3 years. That means in 1 year, it's reducing by a third of that. Okay, or we could look at 100 times 1/2, right? 1/2 to the 1/3, because it's reducing by 1 out of those 3 years that it reduced in this whole interval. So this is where the 1/2 is coming from. It's half of that amount. And then we need 1 out of those 3 years. So 100 times 1/2 to the 1/3 would give us about 79.4. Then we could do to the 2/3 to get this next one, 2 out of those 3 years. And we'd get 63 about. So when you're reducing these, you can be, looking at it like this. You can also be looking at it as like reducing it by the cube root of a half, so that you can be dividing by the same scale factor if you wanted to be. So if we looked at it that way, right, because you're doing 3 equal chunks here, so you want to be reducing it by the cube root of 1/2. So that would be a growth rate between years of 0.7937. So you can also be taking 100 times this growth rate of 0.79. That would get you here. Then taking the 0.79 times this again. Okay. And then the 63 times the 0.79. So now we could do 50 times 0.7937, which would give us about 39.6, and then multiply by 0.7937 again, since that's the growth rate per year, and get 31.5. So then kind of this generic form up here is where you're getting writing an equation for it. So that this way kind of helps you think about writing the equation, because then you'd be at 1/2 to the year divided by 3, right? So we were doing the 2/3, 3/3, 4 would give you the 50, 4/3, 5/3, 6/3 for each of these. So now it's saying in part B, which substance B is modeled by this function, where T is the years since the first measurement. So which substance had a larger initial value? So remember, initial value in the table we can see is 100 for substance A. In the function, it's this number out here, so it's 125. So substance B had a larger initial value at 125 versus 100. And then part 2 of that, which substance is decreasing at a faster rate? So we have this one, substance A. So here's substance A, has a growth factor of 0.79, which means that it's decreasing at about 21%. Then substance B has a growth rate in here. So we got to kind of figure this one out. So we want to do 2 to the negative 1/4 power to figure out 1 year's rate. So if we do 2 to the negative 1/4 power, we get a yearly growth rate of 0.84. So for substance B, its growth factor is 0.84 per year, which is a decrease of 16%. Since this is like 79%, 100 minus 79 is 21. 100 minus 84 is 16%. So substance A is decreasing at a faster rate. Number 8, the value of a collectible sports card grows exponentially. The 2 points on the graph show the sports card's value and its value after 5 years. So we have this 0.70 here. So let me just write 0.7 and then 5.14. I know they're kind of hard to see, so let me just write those 2 points out. What is a reasonable estimate for how much the card is worth after 3 years? So we can go to the table here at 3, okay, and see where it touches. So when we're on this graph, go to 3 years, see where it touches the graph, and then go over. So something a little over $10. So maybe you just say like $10.50, but anything just a little bit over 10. Express the sports card's value S in dollars after T years. So now we need to write an equation here. So we're going to need to figure out kind of our growth factor. And we can see here that this is doubling in 5 years. So we can use that. So the growth factor equals 2 for 5 years. So they want us to write it as S of T. The initial value is 7 because at year 0 it was worth $7. And then it doubles in 5 years. So then we could do T divided by 5 up here to account for that. And that would get us an equation. You could also figure out what it did in 1 year. So if the growth factor in 5 years is 2, you could do 2 to the 1/5 power to split that into equal parts, to split that growth factor into equal parts and get a growth factor of 1.1487 per 1 year, in which case then your equation would be S of T equals 7 times that 1.1487 to the T. So this would be for 1 year. This would be kind of, you can still put 1 year in here, but it's using the growth factor of 2. So write an expression that represents the card's value after 11 years. And so it would be S of 11, because it's going to be 11 years, equals 7 times 2 to the 11/5 power. Or again, in this one, if you were using it kind of the per year here, you'd have 7 times 1.1487 to the 11th power. So both of those are going to kick back the same value. Number 10, the graph shows the growth of an insect population over a period of weeks. The coordinates of A are 210 and C is 540. By what factor did the population of insects increase in the first 3 weeks? So from 2 to 5, how much, by what factor did they increase? So then we would take 40 divided by 10, and we get that they increased by a factor of 4 in those first 3 weeks. So 10 times 4 gets us to 40, so multiplied by 4. What factor did the population change over 1 week? So if this is the change in 3 weeks, okay, then we would split this factor into 3 equal parts. So it'd be 4 to the 1/3 power to get us 1 week's growth. So 4 to the 1/3 is a growth factor of 1.587. So write an equation representing the population's growth per week. So population per week is going to equal the initial population, which we need to figure out. So we don't have the initial population, so we're going to need to go back to figuring out what is this initial population. And so we can do that using this weekly growth rate, right? So we're going to take our population here, 10, divided by this weekly growth rate to go back. So 10 divided by 1.587 gives us a population at 1 of 6.301. So then we'll divide again 1 by 1.587 to get back to year 0. We would be at 3.97. So I just went backwards. So if we multiply by the growth rate to move forward, we would divide by it to go backwards. So took this 10 divided by the 1.58 twice. That gives me my initial population of 3.97. Then we're going to multiply that by our growth factor of 1.587 per week. And then you can always, plug in these points that to make sure that your equation works out. So you could always put 3.97 times 1.587 to the second power to see that gives you back. So if I put in 2, I get back 9.998, right? So I'm getting back 210. And if I plug in 5 here, so 3.97 times 1.587 to the fifth, it kicks back 39.9645. So it's giving me back basically 540. So that means that this equation is correct.